a spinning supermassive black hole at the center of our galaxy. I'm Tonya Hall, and joining me is Dr. Giacomo Fragione, Research Assistant Professor and CIERA Fellow at Northwestern University. Welcome, Dr. Fragione.
Well, thank you.
What kind of work does CIERA do?
So CIERA is it's an acronym for Center for Interdisciplinary Exploration and Research in Astronomy and Astrophysics. So what we do there is, as the title says, we do research in astrophysics. So there are many groups at CIERA. There are people like me that dedicate most of the research to work on black holes. And we have a large group of people that is in the LIGO collaboration, that is essentially the collaboration that discovers and finds black hole merging in the universe. There are also other groups that work on something different, like gamma ray bursts and other observational related stuff.
You and your colleague, Dr. Ave Loeb, just published findings on your study of the black hole at the center of our galaxy. Tell us about that.
Yes, so it was a very exciting study that we developed this summer. And it's actually one of the kinds of works I like the most, because it's like the kind of works that you look to the observations and you immediately realize that you can do something with these observations. In our specific case was to use these new observations to put constraint on the rotation, what we call in astronomy the spin of the supermassive black hole. And it was very nice, this work, because essentially we used very simple equations, a very simple approach, and we derived a very nice limit on the rotation of the supermassive black hole in the center of our galaxy.
How far away is Sagittarius A, and how massive is it compared to other central galaxy black holes?
Yeah, so with respect to us, Sagittarius A star is at about 8.3 kiloparsecs. Okay, so it's so imagine that, to give a reference, our orbit around the sun is 1 AU, that's 1 astronomical units. A parsec is 200,000 AU. So 8 kiloparsecs is like 8,000 times the parsec size. So it's much, much farther than our sun. The mass of our supermassive black hole is of the order of 4 million solar masses. So this is, for us, it can be like very massive because it's like 4 million times our sun, but it's actually a small baby compared to other supermassive black holes out there. So there are supermassive black holes that can be as massive as 1 billion solar masses.
How do you measure the spin of a black hole? I mean, what instruments and techniques do you use?
Yeah, so to measure the spin of the black hole, it's not the easiest thing to do. So black holes, according to Einstein relativity, they are described by 2 parameters that is their mass and their spin. Okay, so the mass is somewhat easier to measure compared to the spin because there are many techniques to do that. While for the spin, for example, a way to measure it is through observing the emission from the black hole. For example, if the black hole has a jet, we can measure that. Or this is for supermassive black hole. For smaller black holes, as the ones that LIGO observes merging, you can infer that through the signal you get at the merger. So now for our supermassive black hole, this has been a bit more difficult because we haven't observed a jet so far. Okay, so we cannot put direct constraints on the spin. So our only chance to do that is to observe the motion of the closest stars to the supermassive black hole. So these stars are called in astronomy S stars, and they hang around there very close to the supermassive black hole at the speeds that are a fraction of the speed of light, so extremely high velocities. And so essentially you can constrain the spin of the supermassive black hole looking at the motion of these objects.
What does a black hole spin tell us about the object, the conditions in which they exist, and their effect on nearby stars?
Yes, so the spin essentially tells us the rotation of a supermassive black hole. And in theory, the spin can be either zero, that is no rotating black hole, and t up to unity. This unity is actually in units of the velocity of light. So if you say a black hole has a spin of 1, it means that it's actually rotating at the speed of light. Okay, this is quite surprising because you can imagine that you can say, okay, how can a guy of 4 million solar masses rotate at velocity of light? So this is puzzling for people to think of that, but actually various supermassive black holes have been found to have a very high spin, as high as 0.9. So this means that they are rotating at 90% of the velocity of light, okay? And actually they emit very powerful jets. And for our supermassive black hole, instead, the question is a bit different, is that, so how can we measure this? So in the future, when the Event Horizon Telescope is going to release the data and to give us a very nice picture as it did for M87, we might be able to infer the spin of our supermassive black hole by studying this image. But again, this image can be understood only if proper numerical models are developed. And these numerical models depend, again, on the mass and on the spin of the supermassive black hole. So now the question is, how do we constrain the spin of the supermassive black hole in the center of our galaxy? Okay, so again, as I said, we can use these stars that are very close to supermassive black hole, because according to Einstein theory, whenever a star is very close to a rotating object, so if this rotating object is massive enough, like a very massive black hole, this object can tilt the orbital plane of the star. Okay, till the point the orbital plane of the star coincides with the equator of the black hole. Okay, so this means basically that, you know, if you are somewhere in the space around a rotating black hole that is not within the equator of the black hole will drag you such that at the end of the day, you will end up on this equator plane. And at that point, you will be at peace. So there will be no more drag given by the spin of the supermassive black hole. So, yeah, so, and for the center of our galaxy, we have these stars that are very close to supermassive black hole. And they are on, they lie basically on two roughly perpendicular planes. And so essentially one can ask the question, okay, but if I look to these objects and they are on two orthogonal planes, what about this effect that is called the lens steering effect or frame dragging? So now the point is that if they are on these two planes, it must be that the spin of the black hole is not too high, because otherwise we would not observe today these two planes, because the orbits of these stars would have been reshuffled by today. And so essentially looking at this geometrical and spatial distribution of the orbits of the S stars, you can put constraint on the spin of the supermassive black hole in our galactic center.
So how does our knowledge of black holes help us conduct operations in Earth orbit and develop missions to the Moon and Mars?
Yeah, so what you can think of is that the situation of a star around a supermassive black hole, as we have in the center of our galaxy, is equivalent in terms of mass ratio. What mass ratio, I mean the ratio of the mass of the black hole to the stars, is roughly equivalent to the situation where you have a satellite around the Earth. Okay, and so basically the same effect that the stars that are very close to the supermassive black hole in the center of our galaxy experience, given by this frame dragging effect, satellites that rotate around the Earth experience the same, basically, because also the Earth is rotating. And so essentially we this is the beauty of physics. We can apply exactly the same equations. We have just to change the masses of the objects. But as I said, the mass ratio is roughly the same. And so essentially, we can observe similar effects around the supermassive black hole in our galactic center with the S-stars or either with satellites around our planet.
Dr. Giacomo Fragione, Research Assistant Professor and CIERA Fellow at Northwestern University. Thank you so much for joining. If somebody wants to connect with you, what's the best way they can do that?
Yeah, so I have a website. So if you just type on Google my first and last name, the first entry should be my website, and the second entry should be my page at CIERA Northwestern. So at there you can find all my emails and Skype and Zoom, whatever, and feel free to reach me any moment.
Sounds good. Thanks again.
Thank you.
And find more of my interviews right here or at tonyahall.net. Thanks for watching.